The goal of a mathematical simulation technology is to model the world, or parts of the world. A basic model consists of a system of material bodies interacting by forces. To describe a one-dimensional world consisting of a straight line, we introduce a coordinate system, specifying points on the line by distance to an origin. The coordinate system allows us to keep track of position and velocity of material bodies. What remains is to specify forces on material bodies. There are dynamic forces given by Newton's second law. The force F is equal to acceleration A times the mass m of the body. And there are internal forces between bodies, transmitted by, for example, elastic springs according to Hooke's law. Altogether, the basic model is a body force or mass spring model, like a two-body problem or a three-body problem. Or it can be a many-body problem, for example, a web of bodies connected by elastic springs, subject to dynamic forces, internal elastic forces, and gravitational force. The web shows a complex pattern of motion, including propagating waves. Here is another many-body system in action, which, when dressed with the skin, gives a simulation with realistic motion. Next, we see a many-body system of fluid particles interacting by viscous forces, which gives a realistic simulation of the splash of a drop into a fluid surface. Here is the Surgeon simulator, built on the same principle, the most popular computer game this year, allowing you to practice heart transplantation on your laptop. Very instructive.
Yeah. Nope. No. Yeah.
To the main message of the Mathematical Simulation Technology program, which is, you can yourself construct simulations of the world by telling the computer what to compute. To tell the computer what to compute, we have to specify laws of motion and laws of forces. Newton's second law of motion connects force to acceleration and mass. We solve Newton's laws or equations of motion by time stepping. We compute the change over a unit of time or time step dt, for example per second, by repeated successive updates of force, acceleration, velocity, position, followed by restart with new force from velocity position. The force is given by present position and velocity. With the force given, we compute a new acceleration, a nu, from Newton's second law. Next, a new velocity, v nu, is computed from the new acceleration, a nu, by adding the increment, a nu times dt, to the old velocity, v old. This means that the velocity increment, dv nu, as the difference, v nu minus v old, equals a nu times dt, that is dv equals a dt, or dv over dt equals a. Next, position x is similarly updated from velocity v with position increment dx equal to v times dt, or dx over dt equal to v. We can now summarize time stepping in these formulas, with successive updates of force, acceleration, velocity, position, force, which is repeated with the chosen time step from a given initial position velocity until the final position velocity at the final time is reached. We notice the following features of time stepping. Each time step is a simple update from addition and multiplication of numbers. There are many time steps and many bodies and many forces. It's good for a computer, bad for a human being. A human can do only the two-body problem. The computer, a big one, can do the n-body problem, with n trillion or more. Time stepping consists of two steps: gather forces and move bodies according to Newton's laws. So it is simple in principle, just gather forces and lift weights according to Newton's laws. Time stepping is a combination of theory or soul, that is, planning the step according to a formula, and practice or body, that is, taking the step by performing a computation according to the formula. By time stepping, the motion of the planets in our solar system can be computed using Newton's law of gravitation. This made Isaac Newton master of the universe because he could solve the two-body problem and prove Kepler's laws from one single law. In the Millennium Run, the formation of galaxies after Big Bang was simulated as an n-body problem with n equal to 10 to the 10. The scientific and industrial revolution was initiated by the calculus of Newton and Leibniz in the late 17th century. The fundamental theorem of calculus expresses the essence of calculus as the relation between derivative and integral. We shall now see that the fundamental theorem can be viewed as resulting from time stepping. We recall that acceleration a is equal to change of velocity dv per time step. That is, a is equal to dv over dt. Similarly, velocity v is equal to change of position dx per time step dt. That is, v is equal to dx over dt. This leads to the notion of derivative. Velocity as change of position dx per time step dt is the derivative of position. Similarly, acceleration as change of velocity dv per time step dt is the derivative of velocity. The integral results by summing increments of the form derivative times dt. The final velocity v final is equal to the initial velocity v initial plus the sum of all velocity increments dv of the form acceleration a times dt. Similarly, the final position is equal to the initial position plus the sum of all position increments dx of the form velocity v times dt. As follows, with the s-like integral sign as a form of summation sign. One way of expressing the fundamental theorem is to say that the total traveled distance is equal to the sum of the steps taken. Here we can follow the steps of Usain Bolt when setting a new world record for 100-meter dash. Usain Bolt won because his increments per time step were longer than the others. Simple to say, but less easy to do. The fundamental theorem states that any function is equal to the integral of the derivative of the function. Or the other way around, the derivative of the integral of a function is equal to the function. The main mathematical question is the dependence of the integral and the derivative on the time step dt. This question can be given a fairly simple answer. Solving the equations of motion by time stepping for different forces, we can construct or compute all the so-called elementary functions, polynomials, the exponential and logarithm, trigonometric functions. More generally, we can construct models of the world by time-stepping body force systems as the essence of mathematical simulation technology. In studying those constructed models, we can learn about the world for purposes of prediction and control. Solving dx over dt equal to 1, you get x of t equal to t. Solving dx over dt equal to 2t, you get x of t, t squared, a quadratic function. Solving this system, you get the trigonometric functions sine and cosine. Solving these equations, you get the exponential and the logarithmic function. And so on.